In this video, we'll be talking about the average rate of change. First, let's define net change, which refers to the overall change in a quantity or value. Suppose you have a function f of x on a closed interval from a to b, where a is less than b. Then, the net change is equal to f of b minus f of a, or, in other words, the final value minus the initial value for whatever thing you are measuring or quantifying. A hotly debated issue is the topic of the federal minimum wage, the lowest amount of money a person can earn for a job as permitted by law. Let's take a look at what the minimum wage has historically been in the United States. The source for these numbers is the U.S. Department of Labor. So in the top row, we have the effective year, and then below that, we have the minimum hourly wage in US dollars. So this video is being recorded in the year 2024, and you'll notice that the federal minimum wage is $7.25. And you'll also notice that that was the same federal minimum wage in the year 2009. There are several different observations that we can make from the data above. In general, one thing that the data tells us is how things change or don't. For example, from 2009 to 2024, again, 2024 is the year that this video is being recorded, the national minimum wage has not changed at all. Another observation that we can make is that from 1974 to 1979, the minimum wage increased by 90 cents. From 1979 to 1990, the minimum wage also increased by 90 cents. In other words, their net changes were the same amount. However, that's not really a fair comparison since those intervals of time have different lengths. What do I mean by that? Well, from 1974 to 1979, that would have been 5 years passing. From 1979 to 1990, that would have been 11 years passing. And they both increased by 90 cents, but over vastly different intervals of time. So do you think that there's a way that we can compare those changes in dollars while also factoring in the amount of time that has elapsed? Pause the video and think about an answer. So this is where the idea of average rate of change comes into play. From 1974 to 1979, let's look at the net change. And the net change was we would take the value that we had in 1979, which is $2.90. And we would subtract $2. And that ends up being 90 cents, which again is the net change. But what if I also divided this by the difference in the years, so 1979 minus 1974, and then this would tell us that we have a 90-cent difference over the span of 5 years. And if I were to simplify this, if I divided, you could use a calculator, this ends up coming out to 18 cents per 1 year. So the interpretation of this calculation is that on average, between 1974 to 1979, the minimum wage increased by 18 cents per year. I went ahead and I did the same calculation from the years 1979 to 1990. And notice that I have this squiggly line here because it doesn't end up coming out to be a nice number. So I rounded it to the nearest cent, but doing so shows that from 1979 to 1990, on average, the federal minimum wage increased by about 8 cents per year. Now, it doesn't seem like that much of a difference because these numbers are so small, but when you compare them, 18 cents per year and 8 cents per year, this value here is more than double. So essentially, we should be upset about this because the minimum wage is not really increasing at a rate that is in line with what it increased with in previous years. So let's more formally look at the definition for average rate of change. The average rate of change of the function y equals f of x between x equals a and x equals b is given by the formula the change in y divided by the change in x, or the change in the output value divided by the change in the input value, or y2 minus y1 over x2 minus x1. This one should look familiar because this is essentially the slope formula. And then the average rate of change, if we're using function notation, is equal to f of b minus f of a over b minus a. To the right, we can see the graph of a function, and if we connect 2 points that have the x-coordinates a and b, then another way of thinking about the average rate of change is the slope of the line segment that connects these two ordered pairs, and that line has a special name. It is called the secant line. So, to repeat, the average rate of change is the slope of the secant line between x equals a and x equals b on the graph of the function f. That is, the line that passes through the two ordered pairs a comma f of a and b comma f of b. And to the right, we can see a visualization of that line. So going back to our previous calculation, we're essentially calculating the slope, and we can think of this value as y2, we can think of this value as y1, this one as x2, and this one as x1. So in both of these our calculations, we were essentially just calculating the slope of a secant line. Let's look at some more examples. Example 1 says use the tables previously given about the US minimum wage data to answer the following questions. Let's go ahead and recall what those values were. Part A says find the net change and the average rate of change of the minimum wage between the years 1976 and 1990. So for part A, we want the net change first. And when we're talking about net change, remember, one way that we could think about the formula is f of b minus f of a. And so because we're taking values and plugging them into our function, these should both be output values or y values. So this would represent our a value, this would represent our b value, and we're plugging them into their function. So b, if we plug that into our function, the output value would be $3.80. And if we plugged in a, which was 1976, our output value would be $2.30. So if I subtracted those, then we'd finally find that our net change is $1.50. Let's go ahead and calculate the average rate of change now. So the average, I'm going to abbreviate it to average ROC for rate of change, is equal to, and remember, if we're using the function notation, it would be f of b minus f of a over b minus a. And notice that the numerator for the average rate of change actually is just equal to the net change, which we already calculated that in the previous part. So our numerator is going to be $1.50, and then we want to subtract the year 1990 minus the year 1976. So that's going to end up equaling $1.50 over the span of 14 years. Now, if you throw this into a calculator, it's going to be 0.107 and more numerical values after that. But because we're talking about money, let's go ahead and round this to the nearest cent. So this is going to be approximately 11 cents per year. So again, the interpretation of this calculation is that between the years 1976 to 1990, on average, the federal minimum wage increased by 11 cents per year. So just to go ahead and interpret and write our final answer in the form of a sentence, so that we know how to write effective sentences and effective final answers, I went ahead and wrote this out. So you want to make sure that you include the years. So between the years 1976 to 1990, it's also really important that you include the phrase on average. You could either put it here or you could put it at the end. So between the years 1976 to 1990, on average, the federal minimum wage And then another really important word is increased, because we found that the slope was a positive number. When the slope's a negative number, then we know that it's decreasing, but it's positive here. So we say the federal minimum wage increased by 11. And then the units on 11 are also really important because it is a rate of change. So the way that we measure rates of change are something like cents per year. Another example of a rate of change would be like miles per hour. That's another unit for a rate of change. This is just an example. Okay. Part B says find the net change and the average rate of change of the minimum wage between the years 2008 and 2024. Let's go ahead and calculate the net change first. So what we're going to do is we're going to take $7.25, which is the minimum wage in 2024, and then we're going to subtract that by $6.55, which is the minimum wage in the year 2008. And when you subtract those, you end up getting 70 cents. So that is the net change between the years 2008 and 2024. Then we want to calculate the average rate of change, which is equal to the net change, which was 70 cents, divided by the difference in the years, 2024 minus 2008. So that is equal to 70 cents over the span of 16 years. Then we want to go ahead and simplify this by dividing. So throwing that into my calculator, I get that it is 0.04375, but because we're talking about money per year, let's round it to the nearest cent. So this is 0.04 per year. So this represents my average rate of change. Let's go ahead and write our final answer in the form of a sentence. We can say between the years 2008 and 2024, the federal minimum wage increased by about 4 cents per year on average. So I'm highlighting some really important keywords, and those are the things that we need in our final answer. Now, just as a quick reminder, between the years 1976 and 1990, the average rate of change was 11 cents per year. So making the comparison, because Part C says, what thoughts do you have after these calculations? 4 cents per year going to 11 cents per year, that is about 2.5 times more. So again, this is quite upsetting because we are currently, as this video is being recorded, in the year 2024, and the federal minimum wage has not increased for several years. And when looking at the time span from 1976 to 1990, on average, it increased about 11 cents per year, which is, again, 2.5 times more than what it has increased by in the last 15 years or 16 years. Example 2 says, Mr. Kwan somehow managed to get a ticket to a Taylor Swift concert. He can't miss it because what if T Swift asks Mr. Kwan to come up on stage? The venue is 9 miles away from his house, and he needs to get there as soon as possible so that he doesn't miss the opening act. Mr. Kwan goes speeding down the streets in his mom's station wagon. The graph below shows how far Mr. Kwan traveled after certain amounts of time. So here's our graph. The horizontal axis represents time in minutes, and our vertical axis represents distance in miles. Part A says, is Mr. Kwan traveling the same speed his entire trip to his final destination? How do you know? And the answer here is, if you look at the graph, there are two components. There's this line segment here and this line segment here. And we know from the graph that I am not traveling the same speed the entire trip because these line segments have different steepnesses, or a better word for steepness in this context is slope. They have different slopes, so I am not traveling the same speed during my entire trip. Part B says calculate the speed that Mr. Kwan traveled during the first 5 minutes of his trip in miles per hour. So because we have something that looks like something per something, that tells us that we are calculating a rate of change, because that's how rates of change are measured in terms of their units. So if we're measuring a rate of change, then likely we are using the slope formula. Now, what am I using the slope formula on? Well, I'm looking at my rate of change, or in other words, my speed during the first 5 minutes. So I want to go ahead and I want to use this ordered pair and this ordered pair. This first ordered pair is 0, 0, and the other ordered pair is 5, 6. So for part B, I'm calculating a slope, and I'm going to do y2 minus y1 over x2 minus x1. Let's go ahead and call this x2 and this y2, and then this x1 and this y1. So following the formula, I would have 6 minus 0 over 5 minus 0. And let's go ahead and put units on this. So the y values are being measured in miles, and the x values are being measured in minutes. So this is going to be 6 over 5 miles per minute. But remember, the question is asking us to evaluate this or give our final answer in miles per hour. So essentially we're using dimensional analysis, and the way that I teach that in my classes is I make this fancy table chart thing, and I'm going to put minutes in the numerator so that this ends up canceling with that, and I need hours in the denominator because we want miles per hour. So what's the relationship between minutes and hours? I know that there exists 60 minutes in 1 hour, and the way that this table works is we multiply across, so 6 times 60, and then we divide. We can think of this long horizontal bar like a division bar or a fraction bar. Then we divide by the product of the things that are in the denominator. So 6 times 60 would give us 3,600, and then 5 times 1 is 5, so we would do 3,600 miles over the span of 5 hours, which, if you simplify, ends up being 72 miles per hour. So there's our answer for part B. Part C says, calculate the speed that Mr. Kwan traveled between right after 5 minutes to the end of his trip in miles per hour. So from 5 minutes to the end of my trip is here. And so I'm going to do the same thing using these new ordered pairs. And let's go ahead and label them. I can call this one x1, this one y1, this one x2, and this one y2. So for part C, we again want to calculate the slope using y2 minus y1 over x2 minus x1. And I'm going to go through this kind of quickly. So now if I go through and multiply, 3 times 60 is 180 divided by 10 is 18 miles per hour. And that is our speed over the second leg of our trip. That takes place between 5 and 15 minutes. Part D says compute Mr. Kwan's average speed over the entire trip in miles per hour. Now, a lot of times when I ask my students to do this question, they will take their answers from part B and part C and just take the average of those two numbers. If you were about to do that, take a moment to pause the video and think about why that is not the correct answer. So again, if I added 72 plus 18 and then divided by 2, that would be taking the average, and 72 plus 18 is 90, and if we divided by 2, we'd get 45. I'm going to abbreviate miles per hour to mph, and this is not the correct answer, so think about why that might be. Okay, so if you said that the reason that we can't just take the average of the numbers that we found in the previous two parts is because I'm not traveling the same speed for an equal amount of time. So for the first 5 minutes, I'm traveling 72 miles per hour, and then notice that I have another 5-minute segment here, and then another 5-minute segment here. So I'm actually traveling 18 miles per hour for twice the amount of time, or double the amount of time. So why is that? Likely what happened was I was speeding down the residential streets at 72 miles per hour because I didn't want to be late, and maybe I saw a police officer with a speed technology measurement thingy, and I was like, oh shoot, I probably need to slow down so that I do not get a speeding ticket. So that's likely what happened. Also, just really quickly, hopefully you realize that this graph is not very realistic. It says that for the first 5 minutes, during the entire trip for the first 5 minutes, I'm traveling 72 miles per hour. And then for the last 10 minutes, for that entire 10 minutes, I'm traveling at exactly 18 miles per hour, which is very unrealistic. So just a quick side note, if we were graphing this, here's my y-axis, here's my x-axis, a much more realistic graph would look something like this, where it's not comprised of two straight line segments. So there's two different ways that we can go about this, at least two different ways I'm going to show you right now. So one way is that if we continue to think about this being broken into 5-minute increments, then we can do 72 plus 18 plus 18, and then divide this by 3. And if we do that, you end up getting 36, and then our units on this is going to be miles per hour. But let's go ahead and do it the second way, which is the way that we've kind of been doing average rate of change throughout this section. So what I've done here is I've created a line segment that connects the first ordered pair to the last ordered pair. And remember, this line has a special name, and it's called a secant line. So the average rate of change is going to be our slope of our secant line. And the first ordered pair is 0, 0, and our last ordered pair is 15, 9. So I can call this x2, and then y2, and we can call this one x1 and y1. So for part D, we'd calculate the slope, which is equal to 9 minus 0 over 15 minus 0. So this is going to end up equaling 9 miles over the span of 15 minutes. And if I want to change this into miles per hour, I can now cancel out the minutes, and this is going to end up also equaling 36 miles per hour. So this represents my average speed over the entire trip in miles per hour. And that concludes this example. Example 3 says, find the net change and the average rate of change for the function f of x equals x squared minus 4x minus 12 on the interval from 0 to 6. So on this interval, 0 is our a value and 6 is our b value. And remember, for net change, the formula is f of b minus f of a. And in this scenario, f of b would be f of 6 and minus f of 0. So I'm going to come off to the side here and evaluate each of these things. So f of 6 in this function, anywhere I see an x, I'm going to replace with 6. So 6 squared is 36, 4 times 6 is 24, and if you simplify this, this is going to end up being 0. Let's go ahead and evaluate f of 0 now. Now notice that our function f of x is a quadratic function, and if we plug in 0, just like any other instance with a quadratic, the first two terms, assuming that it's in descending order of powers, would disappear, and we would just be left with the c value, which in this case is negative 12. So there we have our two values. So f of 6 is 0, and then we're subtracting off negative 12, and that is going to give us a value of positive 12. All right, now let's calculate the average rate of change, since we found that the net change was 12. And I've gone ahead and I've written the formula. Oops. And remember, f of b minus f of a is the net change, which we just got done calculating. So in the numerator, I'm just going to go ahead and put 12. and then b minus a would be 6 minus 0, or just 6, and this is going to end up equaling 2. So our net change in this example is 12, and our average rate of change is 2. Example 4 says find the net change and the average rate of change for the function r of x is equal to 1 over x plus 7 from x equals 3 to x equals 5. So we're doing the exact same thing that we did in the previous example. Let's calculate net change first. We want to do r of 5 minus r of 3, because x equals 3 represents our a value and x equals 5 represents our v value. So this is equal to 1 over 5 plus 7 minus 1 over 3 plus 7. This is the same thing as 1 over 12 minus 1 over 10. How do we subtract fractions? We need to find a common denominator. I'm going to go ahead and multiply this second fraction by 6 over 6 and this first one by 5 over 5. If we do that, we get 5 over 60 minus 6 over 60. These now have a common denominator, so I can go ahead and subtract. 5 minus 6 is negative 1, so my final answer is that the net change is negative 1 over 60. Now let's go ahead and do the average rate of change, which my numerator is the net change, which is what we just found, and then I'm going to divide this by b minus a, which is 5 minus 3. So I have negative 1 over 60 divided by 2, which 2 I can think of as 2 over 1. This is now a complex fraction because I have a fraction over a fraction. The way that we deal with those is we keep change flip. So I keep the numerator, I change the denominator, and I change it by flipping it or taking the reciprocal. And I can multiply these even though they have different denominators because I just multiply across. So negative 1 times 1 is negative 1, and then 60 times 2 is 120. So this is going to end up equaling negative 1 over 120, and that is the average rate of change for this question. Example 5 says find the net change and the average rate of change for the function f of x equals the square root of 3x minus 8 over the interval 4 to 11. So let's go ahead and start with the net change. I'm going to do f of 11 minus f of 4. So that's going to end up equaling the square root of 3 times 11 minus 8 minus the square root of 3 times 4 minus 8. And that is equal to 3 times 11 is 33. 33 minus 8 is 25. And then 3 times 4 is 12. 12 minus 8 is 4. So this is going to end up equaling 5 minus 2, which is equal to 3. Now let's move on to the average rate of change. We're going to have the net change, which we just calculated to be 3, over b minus a. So that's going to be 11 minus 4, which is going to be 3 over 7. And that's our final answer. And that concludes this video. Thanks for watching.